Hello and welcome to part 9 of Dev Maths and Stats Refresher Course, Lecture 5. We're looking at optimization under constraints, first of all with equality constraints. Can't open this as usual. So we're going to restart the whole thing. And in the previous section, when we found the minimum points of this function here, we placed no restrictions on the possible values of x and y. So the value of 1630 we got above is actually the global minimum value of the function, as we implied from looking at the second order conditions. We found that the Hessian matrix was fixed, so it's a global minimum. Okay, suppose, however, that we want to find the minimum value of this function, and there's also an extra condition. I'll start with a really complicated looking one. That y squared plus 2x squared must also be equal to 1024. So you've got to find the minimum of this and also stick on this condition, so that's always satisfied. So one thing you can do, one way to do that is to rearrange this to find y is equal to, then substitute that back into here for y, and then try and find an unconstrained solution to that. However, that would be incredibly complicated because y is going to be equal to 1024 minus 2x squared, all square rooted, and then that's going to occur through here. So it would be horrendous. So we're going to use a method that gets around that. It's called the method of Lagrange multipliers. Okay, now to see how this works, you've got to look at the one of the graphs we've been looking at before. So as you see, this can be set up like linear algebra in a very kind of standardized way, so you can just go through the same steps every time. So we're going to start with defining the function we're trying to optimize as f, and the constraint itself we define as a function, and you'll see why that is done, particularly in the next section on inequality constraints. F is often called the objective function. So when people, in the aid industry and so on, talk about the objective function, they're talking about nutrition or welfare or educational goals. So that's the thing you're trying to maximize or minimize. And G is defined deliberately separately from the constant. You'll see what I mean when I go through the commands here. So that's how you set up the initial two things of the constraints. So that's the objective function, and that's the constraint. Notice I haven't put the 1024 in, I've just defined the function. And then here's the graph. So hopefully this will show you the situation we're trying to work with. Okay. So, as before, here's the graph. And if it was just, okay, minimize this, you could use the same thing, find the first order conditions, and you find that the answer is around here. Okay. However, now we're not allowed to do that because now the constraint says you must stay with these combinations of x and y that satisfy the equation that g is equal to 1024. So you have to stay on here at the same time as staying on that black line, combinations of x and y, find the minimum value of this function. So you can see that it's going to be round about sort of here somewhere. So you just want a way of pinning down where this is, that point, because that's the lowest you can get in the constrained optimization in this case. To try and visualize it a bit better, what I'm going to do on the next one is just add another line on. And this line shows you, if I stick on these points here, which other points I can get to on the graph. So I've just gone straight up from the black line to these points. So here again, here you can see that's the point you want, just there. That's the lowest point you can get to. So how do we define that? Okay, and this is the way that it works logically, and it's a clever trick to do with gradients. And to help do this, we're going to move that round to this position, that, and so if I take this to the whiteboard, then I can try and explain what the text is going through there. That the idea is, if I start at any point at all, like this, then if I move in some direction, like this, say, this could be dx and dy. In this example, if I move in this direction, then the dx would be positive and the dy would be negative because I'm going in this direction. But it could be in any direction at all. Now the change in the function will be given by fx, fy, this is the gradient vector times dx, dy. So it's the dot product of this direction I'm moving in multiplied by this vector of partial derivatives will give me the change in the function. Also over here, that as well as the function's value, I could find the value of this constraint, and it would not be 1024 because I'm not on the line. But the change in g, the constraint function, would be gx, gy, those partial derivatives, times the direction I'm moving in. Okay, so if I start at some point like this, if I move, say, in this direction, so here, if I move along from this position, moving along the constraint line, then this one here would have to be 0. Because moving along the constraint line, the constraint is not changing. So from any position on the constraint, if I move along it, this would have to be 0. Now if you remember your dot products, that means that this dot product would have to be 0. So this and this have to be at 90 degrees to each other. So this vector here could perhaps be pointing in this direction. I don't know how big it is. It could also be pointing in this direction, but it's on this line somewhere. And that, I should give you a notation for this. This is grad to G. That's F and that's G. Oops. The name of these two vectors, shorthand. So this vector must be pointing at 90 degrees in this direction. However, what we can see here is that if I moved in this direction, I'm getting close to the maximum. So this would be positive, okay? Which means that, if you remember from what that means about the angles, it means the angle between the direction I'm going in and this vector here would have to be less than 90. So this other vector, which I call grad F, it would be pointing upwards towards the top point here. So that could be something like this. Actually, this is a minimization problem, isn't it? Okay, so it'd be pointing this way because it's pointing upwards like this. So below what we said, this would be this direction, because if I'm going in this direction, the function will actually be decreasing because this is the minimum. So if I'm going towards this, I'm going down. So this dot this would have to be negative. So I must be going in a direction away from this. So this F is pointing somewhere over here. But anyway, that's of secondary interest, because what I want to do is say what happened at optimum on constraint, which is the point we're trying to look for here. That's the point we're really trying to identify. Again, if I move in this kind of direction, I must be not changing the constraint. So as before, this must be, the delta G must be pointing in this direction, so it's at 90 degrees here. But also, if I'm at my best point on this line, if I can't improve this, then also this must be 0, because if this was 0 and this was positive, then I'd like to Actually, I'm trying to find the minimum. If this was 0, this was negative, I'd like to move a bit more in that direction to get the function down. But I can't do that because I'm at the best point. So this must also be 0 at an optimum point, as well as this, which means that this must be 90 degrees to this. So if this is at 90 degrees to this, and this is at 90 degrees to this, the conclusion is that this is 90 degrees, this is 90 degrees. These two are on a straight line, they're parallel. So at the optimum point, these two must be parallel at the optimum point, because moving along the constraint line does not change the function, because I can't get any better or worse. I'm trying to get higher or lower, and it doesn't change the constraint because I'm not allowed to change the constraint moving along that function line, that constraint line. So the key insight is that these two must be parallel at the constrained optimum, which is what is explained here. So if this is parallel to this, if one vector is parallel to another vector, then the second vector must be a multiple of the first vector. And we usually have it this way around, so that the function vector of partial derivatives must be some constant, which we call lambda traditionally. Lambda is a Greek letter, a constant times the partial derivative vector of the constraint function. In other words, this must be lambda times this, and the x derivative must be lambda times the x derivative of the constraint, and the y derivative of the function is lambda times the y derivative of the constraint. And the Lagrangian method, which we'll go into in the next session, cleverly combines these two things together, along with the constraint itself, to give you first order conditions with equality constraints. So that's what we'll look at in the next session. So thanks for watching.